Why do spikes form on ice cubes? Picture this. You reach into your freezer, ready to add a few cubes of ice to your drink. Most cubes look perfectly normal, solid, square, predictable. But every once in a while, maybe 1 cube in 100, something strange catches your eye. A tiny spike, like a miniature tower, rises from the center of the cube. It looks almost magical, as though the water molecules had been climbing an invisible ladder while you weren't watching. What's happening inside your freezer? Why do ice cubes sometimes grow spikes, and why is it so rare? To answer that, we need to take a closer look at one of the most familiar, yet still surprising, substances in the universe: water. Water is not like most liquids. In fact, it breaks some of the most basic rules we might expect. Normally, substances contract when they freeze. But water, it does the opposite. When it freezes, it expands. That expansion is the key to understanding ice spikes. Here's the sequence. When you place a tray of water in your freezer, the first thing to freeze is the outer layer, the sides of the cube and the top surface. Think of it like building a shell. The outer layer hardens into ice, while the inside remains liquid. Now, as the liquid interior begins to freeze, it expands, but the outer shell of ice is rigid, leaving the water trapped with nowhere to go except through the weakest point. If there's a tiny hole left in the surface ice, pressure pushes the still liquid water upward through it. As the escaping water reaches the cold air, it freezes, forming a slender spike. Slowly, drop by drop, the spike grows higher until the last bit of liquid is gone. It's like a fountain that freezes in mid-spray. If this explanation sounds simple, the rarity of ice spikes adds a twist. Why do we only see them once in a while? The answer lies in the delicate balance of conditions required. Imagine trying to bake the perfect souffle, just the right temperature, timing, and ingredients. Ice spikes are nature's souffle. Asterisk temperature matters. If the freezer is too cold, the entire cube freezes quickly and evenly, sealing off the top before a spike can form. If it's too warm, the cube freezes too slowly, and the liquid doesn't build enough pressure to escape. The sweet spot is when the cube freezes just slowly enough for the interior to lag behind the surface. Asterisk shape of the container. A perfect cube tray provides a straight path upward for escaping water, but angled sides or irregular molds make it harder for water to funnel into a spike. That's why certain trays might produce spikes more often than others. Asterisk purity of the water. Tap water, filled with minerals and impurities, tends to freeze in irregular patterns, leaving fewer neat channels for water to escape. Pure or filtered water, by contrast, freezes more smoothly and predictably. This increases the chance of a spike forming. In fact, some experimenters have found that distilled water almost guarantees a higher rate of ice spikes. Even cooling. The tray must release heat in just the right way, both through the sides in contact with the freezer shelf and the top exposed to air. If cooling is uneven, the outer shell might freeze too fast or too slow, disrupting the delicate timing needed for a spike to rise. Because these conditions are so specific, ice spikes remain rare little surprises, even though the physics behind them is universal. What makes ice spikes fascinating is not just their appearance, but what they reveal about the hidden world of phase changes. Every time water freezes, billions of molecules rearrange themselves into a crystalline lattice, expanding as they lock into place. That expansion is strong enough to crack rocks over centuries or burst pipes in winter. In the case of ice cubes, it's strong enough to squeeze liquid water through a pinhole, sculpting a tower of ice. And the spikes aren't just random curiosities. Scientists have studied them to understand how ice forms under different conditions. NASA has even investigated ice spikes as analogs for icy environments on moons like Europa, where water and ice interact in alien conditions. A simple cube in your freezer carries echoes of processes happening across the solar system. So why care about a tiny spike in your ice cube tray? Because it's a reminder that even ordinary experiences hold extraordinary stories. The same physics that makes an ice spike also explains why glaciers carve valleys, why frozen pipes burst, and why life itself depends on the unique properties of water. Water's expansion when it freezes is the reason lakes freeze from the top down instead of bottom up. If ice sank, bodies of water would freeze solid in winter, making life impossible. Instead, ice floats, insulating the liquid below and preserving ecosystems through the coldest months. Ice spikes, then, are like miniature monuments to the importance of water's quirks. They show us how unusual and life-giving this molecule really is. Next time you open your freezer and find an ice cube with a spike, take a moment to marvel. You're not just looking at frozen water, you're witnessing physics in action, a battle of pressure, temperature, and purity has played out silently in your freezer, leaving behind a delicate tower. It's easy to overlook these tiny details in everyday life, but every one of them is a window into the universe's rules. Ask, why? About something as simple as an ice cube. And suddenly, you're exploring the building blocks of matter, the structure of water, and the conditions that sustain life on Earth. That's the beauty of science. It transforms the ordinary into the extraordinary. It shows us that even the smallest spike of ice carries within it the vastness of natural laws. So, the next time you drop a cube into your glass and notice a little frozen tower poking up, don't just think of it as a quirk. Think of it as nature's way of whispering, there's always more to see. If you only ask,